The sun's not only the most massive object in our solar system, but it weighs more than everything else in the solar system put together. Take all the major planets, their moons, the asteroids, comets, put it all together, it weighs less than the sun. Now, if you look at the major planets, you find most of them are moving in the same way. They revolve around the sun in the same direction and they spin on their axis in the same direction. Venus is an exception in that it spins backwards. And Uranus might also be an exception, but Uranus is so tilted we're not quite sure which way it's spinning. We can divide the planets into inner and outer planets. The inner planets tend to be small compared to the outer planets. They tend to spin slowly on their axis, which gives them long days. They tend to have very few moons. Mercury's got no moon, Venus no moon, Earth one moon, Mars two moons. They tend to be rocky planets, crusts of silicate rock, cores that are denser than the mantle, and so we think that they're kind of like Earth and that they're mostly rocky with an iron-rich core. Mercury and Venus, being closer to the Sun than we are visible only in the morning or evening. And also, being closer to the Sun than we are, they show phases when viewed from the Earth. Mercury is a cratered, airless hunk of rock, looks a lot like our Moon. Now, being the closest planet to the Sun, it's got the shortest year, and it's also got a very high daytime temperature. Of course, without an atmosphere, at night it cools down rapidly. In terms of size and mass, Venus is Earth's twin, but in other ways it's very different. Remember I said it's got a very slow backward spin, and in fact it's so slow its day is longer than its year. Now Venus has got an atmosphere, but it's very different from Earth's atmosphere. It's a thick atmosphere of carbon dioxide with clouds of sulfuric acid droplets, and these clouds completely cover Venus. So the surface of Venus was a great mystery until radar was invented, and the radar can punch through the clouds, and so now we know what the surface of Venus looks like. This carbon dioxide rich atmosphere also has another effect, a tremendous greenhouse effect. Even though Venus is farther from the Sun than Mercury, its surface temperature is comparable to that of Mercury. Radar has allowed us to punch through the clouds of Venus to map the surface. And one of the outstanding features of the surface of Venus are all its volcanoes. Lots of volcanoes, but one of the things we don't know about those volcanoes is, are they dormant? We haven't observed any of them erupting, and we're not quite sure if Venus has active volcanoes at the moment. The Earth's moon's a fairly good-sized moon, especially given the size of the Earth relative to some of the other planets. Takes just under a month to go once around and is tidally locked. By tidally locked, we mean that the time it takes to go around the Earth is the same as the time it takes to spin on its axis once completely around. So we always see the same face of the moon. Now this tidal locking is because of gravitational interactions between the Earth and the moon. The Earth's gravitational interactions have slowed the spin of the moon down to where it's tidally locked. But the moon has also gravitationally interacted with the Earth and is slowing the spin of the Earth down. Our days are a little bit longer than they were back in the days of the dinosaurs. The most obvious feature of the moon, of course, is craters and moria, the large dark areas that the ancients called seas and oceans. Those dark areas are actually large basaltic lava flows. When the Apollo astronauts brought back the rocks, they were radio dated, and it was found that the ages of the rocks varied from about 3 billion years up to about 4.6 billion years old. No young rocks. So no igneous activity apparently for the last 3 billion years. It's also been found by the seismic devices that were left on the moon that there's not much in the way of moonquakes. Furthermore, other measurements have revealed that the moon has no magnetic field. However, when we look at the rocks and do the paleomagnetism trick on the rocks, we find that when those rocks were formed, the moon did have a magnetic field. All of this evidence seems to suggest that the interior, the core of the moon, has cooled down and the moon is now geologically dead except for more cratering. As the moon orbits around the Earth, the side of the moon facing the Earth will either be sunlit, and we call this a full moon, or partially sunlit, or completely shadowed, and we call that a new moon. In order for there to be a solar eclipse, the sun, the moon, and the Earth have to be in a direct line. Because the orbit of the moon is slightly tilted, the moon will only be perfectly lined up with the sun and the Earth about twice a year. Now, the orbit of the moon is also elliptical, and so sometimes it's a little closer to the Earth and looks a little bigger, sometimes a little bit farther away and looks a little smaller. So we can have a total eclipse where the moon completely covers the photosphere of the sun, or an annular eclipse where the moon doesn't quite cover the photosphere. There's a tiny little edge of the photosphere that peeks out. In a lunar eclipse, the Earth's shadow falls on the moon, and so we have to have the sun, the Earth, and the moon once again in a line. Our current best theory for the origin of the moon proposes a glancing collision between an object bigger than our moon and the Earth. Some of that material from that object gets transferred to the Earth in that collision. Some of the material rebounds, ends up in orbit around the Earth, and coalesces to form our moon. Mars is about 1.52 astronomical units from the Sun. An astronomical unit is the average distance of the Earth from the Sun. So Mars is about half again as far from the Sun as we are. So not surprisingly, its year is almost double our year. One neat thing about Mars is its day is almost exactly the same as ours. It's only a half hour longer. I think I'd like living on Mars, having that extra half an hour. Mars is about half the size of the Earth and quite a bit lighter. With a thin atmosphere and no liquid running water for erosion, it's not surprising that the surface of Mars shows lots of craters. This particular crater is known as the Happy Face crater or Have a Nice Day crater. Mars also has some volcanoes, some of which are truly spectacular. Olympus Mons is the biggest volcano in the solar system. It also has some spectacular fault systems. The Valles Marineris is a huge fault system dwarfing anything we have on the Earth. NASA has landed several rovers on Mars, which have allowed scientists to investigate the nature of the surface of Mars in detail. Like Venus, Mars has an atmosphere of carbon dioxide. Unlike Venus, Mars's atmosphere is very thin, and just not a whole lot to it. There is enough there, though, to make for dust storms and for clouds. The atmosphere, however, is so thin that it doesn't keep much heat in at night. It gets very cold at night, even though the daytime temperature at the equator, anyway, isn't too awful. It's cold enough at night to freeze out some of the carbon dioxide. In fact, the polar caps of Mars are a mixture of frozen water and frozen carbon dioxide. The Martian atmosphere is very thin, but it can still generate some of the phenomena we're familiar with here on the Earth, like dust devils. Is there any life on Mars? Well, we haven't found any yet, but we're going to continue looking. Current conditions on Mars are pretty harsh. The atmosphere is very thin, it gets very cold at night, pretty rough for something to survive. There's no liquid water on the surface, but there might be some under the surface, maybe in the form of a permafrost of some sort or other. Also, Mars may have been wetter in the past. There's some interesting erosional features that some scientists say suggest that there might have been surface water on Mars in the past. May have had a little thicker, heavier atmosphere in the past. There's also a meteorite that has some real interesting features to it that came from Mars. And some scientists, once again, think that some of those features may have been generated by Martian microscopic life. So bottom line is, we haven't found anything yet, but we're interested in thoroughly checking out Mars to see if there might be or might have been. In 1877, Hall spotted two tiny little moons orbiting Mars. Now, to appreciate just how tiny these things are, you have to realize Galileo started using a telescope back in 1609. So you've got over 200 years of people looking at Mars with telescopes. It wasn't until 1877 that Hall spotted those moons. All of the outer planets except for Pluto are very large, have low density, and the reason they have low density is that they're ocean planets, liquefied gas, and that gas is liquefied is mostly hydrogen and helium, real light stuff. Now we think there's probably a small rocky inner core, but we're not sure. Now in addition to the liquefied gas, above the liquefied gas you've got an atmosphere, once again, largely hydrogen and helium, and there's clouds. These outer planets, once again except for Pluto, are completely covered with clouds. So when you look at a picture of one of these planets, Jupiter, Saturn, Uranus, Neptune, what you're really seeing are cloud tops. These large planets spin rapidly on their axis, and so they have very short days. They typically have lots of moons, and surprisingly enough, they have rings. For a long time it was thought that Saturn was the only planet with rings, but it turns out that Jupiter, Saturn, Uranus, and Neptune all have rings. Jupiter is over 5 times as far from the Sun as we are, and takes almost 12 times as long to go around the Sun. But look at its day. Its day is less than half the length of our day. Now, Jupiter is truly a huge planet, but look at the density, 1.33. Remember, our density is over 5. Jupiter has a thick atmosphere, mostly hydrogen and helium, but smaller amounts of other things such as ammonia, methane, and water. Also has thick layers of clouds. Remember, Jupiter's covered from pole to pole with thick clouds, and that's what you see when you look at a picture of Jupiter, are the cloud tops. When you look closely at a picture of Jupiter, you notice the clouds are in bands. Those are convection cells. Rising atmosphere and sinking atmosphere. With all that convection, it's not surprising you also have storm systems. And the most famous storm system on Jupiter is the Great Red Spot. Now back in 1660, Cassini noticed something on Jupiter that he described that sounds like he was describing the Great Red Spot. And if that's the case, the Great Red Spot's been around for hundreds of years at least. Jupiter's got the current record for most number of known moons. That's current. Every semester lately I've been having to edit these slides because the astronomers keep finding more moons. Now the most famous of Jupiter's moons are the ones discovered by Galileo. There's 4 of them: Io, Europa, Ganymede, Callisto. They're interesting because they're each a bit different from the others, geologically speaking, and they're all quite a bit different from our moon, geologically speaking. And so if you've seen one moon, you really haven't seen them all. Io is the only object outside the Earth where we know that there are active volcanoes because we're constantly seeing them erupt on Io. In both of the pictures I show you, there's images of volcanic eruptions. On the one on the left, you see a volcanic lava plume erupting on the edge of the planet, and in the other one down below you can see an active caldera with the glowing magma. Now, the magma on Io's got lots of sulfur in it, and this gives Io kind of a yellowish, orangish, reddish appearance. What keeps these volcanoes active? After all, our moon hasn't had a volcanic eruption in 3 billion years. Its core has cooled off. What's keeping Io warm, it appears, is gravitational interactions with Jupiter. Jupiter has an enormous gravitational field. And so what Jupiter's doing is causing the crust of Io to have tides, high tides and low tides. The crust is flexing, and that flexing of the crust is heating Io, keeping it volcanically active. Europa is a little bit farther out from Jupiter than Io, and so it doesn't have quite the extreme tidal flexing of the crust that Io has, but it does have a little bit. Those little scratches, those are actually breaks in the crust of Europa. The crust of Europa is made of ice. And this ice, as it breaks, It then refreezes. Now, underneath the ice crust, we suspect there might be liquid water. And if there's liquid water, this makes Europa an interesting place to go looking for life. Ganymede's further out from Jupiter than Europa, and Ganymede is the largest moon in the solar system. In fact, it's so large that if it weren't for the fact that it's in orbit around Jupiter, we'd have to classify it as a major planet. Now, Ganymede seems to be made up of a mixture of rock and ice. It's got lots of bright craters, and it also has some groove terrain that's somewhat reminiscent of Europa's grooves and shattered ice. Callisto is a little bit farther from Jupiter than Ganymede, and Callisto is kind of similar to Ganymede in a lot of ways. It's ice and rock, a little bit more ice, a little bit less rock than Ganymede. It's got the bright craters like Ganymede, but it doesn't seem to have the groove terrain that you see so commonly on Ganymede. Saturn's the next planet out, and it's similar to Jupiter, a little bit smaller and a little bit lower density. Density of 0.71. It's got a density less than that of water, and it is the least dense of all the planets. All of the outer planets have got rings, but only Saturn's rings are really spectacular. Now, for a long time we realized that the rings of Saturn had to be a swarm of small particles because they're too close to Saturn for it to be a single solid object. When you get two large objects close to each other, the gravitational effects will rip one of them apart. Tidal forces. Saturn has at least 60 moons, and the largest of these, Titan, is perhaps the most interesting of the bunch. And what makes it interesting is it's got an atmosphere. You don't normally think of moons as having atmospheres. And even more interestingly, this moon's atmosphere is made up primarily of nitrogen with a good bit of methane gas. And this methane gas has made Titan a rather mysterious object for a long time, because that methane gas reacts with sunlight to form photochemical smog. And on Titan, that photochemical smog is so thick that visible light can't get through it. And so, until NASA and the European Space Agency in 2005 put an orbiter around Saturn with a radar instrument, we really didn't know what the surface of Titan looked like. And so now, that radar can punch through that hydrocarbon smog and show us the surface of Titan. And what it's shown us are areas that look like bogs or lakes. And these bogs and lakes seem to be filled with liquid methane. So, a very interesting object. Enceladus is a small icy moon of Saturn that has geysers. Mercury, Venus, Mars, Jupiter, and Saturn are all bright objects, easy naked eye objects in the sky. Uranus, on the other hand, is a very dim object and wasn't discovered until 1781 when a musician and amateur astronomer, William Herschel, discovered it. His discovery of the planet Uranus made Herschel the most famous astronomer of the day and became a full-time astronomer. Now, one of the more interesting things about Uranus is its axial tilt. All the planets' axes are tilted a little bit, but Uranus is tilted by 82 degrees. It's essentially lying on its side. Herschel's discovery of Uranus led people to wonder if there might be another planet out there beyond Uranus. However, the sky is an awfully big place to look for a tiny little dim object, particularly since in order to prove that it's a planet, you've got to watch that tiny dim object move relative to the background stars and then calculate an orbit for it, showing that that orbit is out beyond the previous planets. Very tedious, time-consuming process. John Couch Adams and Urbain Le Verrier had the same bright idea independently of each other, and that is, use Newton's law of universal gravitation to track down where the next planet should be. The idea is all planets gravitationally interact with each other, and therefore their gravitational interactions cause deviations from the perfect Kepler ellipses. So what you do is you take lots of data of the planet Uranus. You subtract out the gravitational deviations from the Kepler ellipse caused by Jupiter and Saturn. Any deviation that's left has to be due to the next planet out, Neptune. Knowing those deviations, you can calculate where Neptune must be to cause those deviations. Adams-Leverrier did the calculations, predicted where Neptune had to be in the sky. Leverrier's calculations were given to Johann Gottfried Galle, who looked in the sky, spotted Neptune, watched it move, did the calculations for the orbit, and discovered Neptune. Adams wasn't so lucky. The astronomer he sent his calculations to never really followed them up. Uranus and Neptune are almost twin planets, about the same size and mass.
In 2006, the International Astronomical Union decided to create a new category, the dwarf planets. Smaller than the major planets, but big enough to be spherical. Later, they subdivided the dwarf planets into the Plutoids, Pluto-like stuff out past Neptune, and everything else, which turned out to be just Ceres.
After the discovery of Neptune, the rush was on to find the next planet out. A number of people tried to do the universal gravitation trick to find the next planet. However, unfortunately for them, Pluto is way too small to have any noticeable gravitational influence on Neptune, and so those calculations never worked. So it wasn't until 1930 that Clyde Tombaugh found Pluto in a brute force search. Pluto takes 248 of our years to go once around.
Pluto is about half the size of Jupiter's moon Ganymede. Its composition appears to be a mixture of rock and ices, very similar to that of a typical comet. Therefore, the Plutoids may be just very large comets. Given its tiny size, astronomers were surprised in 1978 to discover that Pluto had a moon. But now we know that Pluto has at least 5 moons. It also has a very, very thin atmosphere of nitrogen and methane.
Ceres is the largest of the asteroids and the only one big enough to be classed as a dwarf planet. The asteroids are also sometimes referred to as the minor planets. There's thousands of them out there. The majority of the asteroids are found in a belt in between Mars and Jupiter, the famous asteroid belt. However, there's some others that have different orbits, and some of these orbits come very close to the Earth. The Apollo asteroids, for example, have an orbit that actually crosses the Earth's orbit. It's all a matter of timing whether or not we get hit. The February 15, 2013 Chelyabinsk impact is a reminder that there are a lot of small hunks of rock out there, and while most will miss us, we do get hit occasionally. Comets are a mixture of ice and various frozen gases, all mixed together with rock. A dirty snowball. Most of your comets are fairly small, just a few kilometers across. The Kuiper Comet Belt is a swarm of comets in orbit around the Sun out beyond Neptune. The Oort cloud is a spherical swarm of comets out beyond the Kuiper Comet Belt. Comets have orbits that are highly elliptical and highly inclined. Now, a comet doesn't really look much like a comet until it comes in close enough to the Sun to where the Sun's heat vaporizes some of those frozen gases. The comet ends up having an atmosphere. The solar wind blows that atmosphere away from the comet, generating the tail of the comet. And this is why the tail of the comet always points away from the Sun. The solar wind is moving faster than the comet, and the solar wind blows the atmosphere away, generating the tail. Gravity is universal, so if a comet comes too close to a major planet, its orbit can be altered. And one of the things that Jupiter does a lot, it turns out, is alter the orbits of comets. And Shoemaker-Levy 9 not only had its orbit altered, but it got real close to Jupiter, and Jupiter tidally ripped it apart, ripped it into over 20 fragments. The next time around, Shoemaker-Levy collided with Jupiter, Over a period of about a week, those 20 fragments slammed into Jupiter, generating some spectacular images. Halley didn't discover Halley's Comet. What Halley discovered was that when he plotted the orbits for 2 previous comets, he discovered that they were actually the same comet coming back about every 76 years. So he was able to predict the return of Halley's Comet. We say about every 76 years because, once again, these small objects can have their orbits modified by gravitational interactions with the major planets. Meteoroids are small hunks of rock or metal or carbon that are in orbit around the sun. So as long as it's floating around in space minding its own business, it's a meteoroid. If it runs into the Earth's atmosphere and is burning up through the atmosphere, then we call it a meteor. If it makes it down to the ground, then it's a meteorite. Meteoroids are generated typically by comets. As a comet goes around the sun, a lot of the volatile gases evaporate, spewing bits of rock fragments up into the air, gets left behind as a trail of debris. It's easy to predict when the meteor showers are going to occur. It's just a matter of when does the Earth in its orbit cross the orbit of these meteoroids.